discussed a few things about registers. Then there was discussion about move instruction, some of valid and invalid move instructions. Then some discussion about add instructions. We had a small theoretical introduction to assembly programming of 8051. There was structure, and finally we ended with program counter. So today let us start with data type and directives. Okay. So those of you remember in our previous class, while discussing about the structure of assembly language, we said that there are two things. One is instructions, which are instructions like add, move, increment, decrement, like this, and others are known as directives like org, and there are some other directives as well, so we'll discuss. So your instructions are translated into machine language or opcode, whatever you say, and your directives are not translated into machine code. Rather, they simply give some directions to the assembler. So now we will basically discuss some of the directives, as you see. About the data type, your 8051 means has only one data type, it is 8 bits, and the size of each register is also 8 bit. All right. Now we know that we have seen some 16-bit registers like your data pointer or your program counter. But when it says that the size of each register is also 8-bit, it basically means the registers which are accessible to the user or programmer. Okay, so as a programmer, the registers that we can normally access are all size of 8 bits. So if a designer or a programmer has data which contains more than 8 bit, then it is the responsibility of the designer to break down the bigger data into small chunks of 8 bit and fit accordingly. All right. So let us start with data defined by DB. Okay. So defined by, fine. So origin 500H, you know that this is the starting of the address from where we will start. Data byte 28. If you do not provide any specification as to what type of data this is, like whether it is decimal, binary, or hex, if you do not provide anything, your compiler will automatically assume that this is in decimal format, provided the format is correct. So if it is in decimal format, it will be converted to hexadecimal number, which is 1C by the assembler. Now, if you want to store a binary number, then at the end you need to specify that this is binary, that is you need to specify B. If you do not put this B, this number will again be considered as a decimal number and will be translated by the assembler from decimal to hex. But when you say that this is a binary number, then your assembler will convert this from binary to hex. So this becomes 36 in hex. And if you give in 13, if you give in hexadecimal format, then there is no complication. Now, if you want, you can give characters as well. But the important thing is that whenever you give characters, you need to make sure that you provide the characters with quotation. The quotation can be either single or double. I repeat, the quotation can be either double quotation like this, as you can see, or if you want, you can give single quotation as well. That is totally up to you. So whenever the assembler will see that you have provided some numbers or characters within quotation, then for all the characters or numbers within quotation, the assembler will automatically assign the corresponding ASCII code, and then it will be saved. Okay, so up to this, if there is any confusion or any question, you can ask.
Sir, can you repeat the last sentences about the double quotation, single quotation?
Okay. So this is basically this line. Okay, so if you provide any character or number within double quotation, your assembler will convert that based on the ASCII code. Like when I have written over here L, so the corresponding ASCII code of L will be stored. Then I have written over here I, so the corresponding ASCII code of I will be stored by the assembler. Is it okay? It is not stored like a character, because as we have said, there is only one data type. Okay, so we deal with numbers only. So whatever you give, it has to be converted to numbers. So these characters will be converted to numbers with the help of their ASCII code. Is it okay now?
Yes, sir.
Any other question, please?
Can you repeat the 1C part?
1C part, this one. Okay, so you see that data byte 28. After that, we have not provided anything. Like for binary, we need to give a B. For hexadecimal, we need to give H. For decimal, we need to give a D also. But if you do not give D, in that case, if you do not provide any specification as to what type of number this is, then your assembler will always assume that this is a decimal number. Okay, and it will convert that decimal number into hexadecimal number. Your assembler converts everything to hexadecimal, then it stores. So everything will be converted into hexadecimal format. Is it understood now?
Why the I is there?
This one? This is not I, this is for comment. Before comment, we give a semicolon. Okay? Actually, I should have given a small gap. My bad, sorry. This is a comment. Semicolon.
Yes,
comment. Okay, any other question? Sorry for this handwriting, okay? This is also semicolon. Extremely sorry. Okay, any other question? Okay, so if there is no question, so let's move forward.
Sir, what if we don't define the org command here?
Okay, what if you don't define the org command here? Then by default, you are supposed to encounter an error message. Again, some assemblers might overwrite or might overrule this instruction, but this is mandatory for your 8051 microcontroller assembly language. You have to provide the origin from where it starts. The significance is something like this. See, okay. By the end of this class, you will see an example that will deal with this thing. Inshallah, at that time it will be clear. Okay. So for the time being, just keep your question within yourself. You will understand the significance of this thing, inshallah, by the end of this class. Okay. Inshallah. So moving on. Just a second, it might be someone from your batchmates. So origin has already been discussed. So it indicates the beginning of the address, and someone had a question. Inshallah, you will see an example at the end. Don't worry. Now, the important thing to mark over here is this portion. Like if H is absent, if I go back to my previous page, sorry, those who are writing, I'll come back. Don't worry. You see that after writing the number, we always provide H. However, if H is absent, the assembler will convert that into hex, assuming it to be decimal. This is an important part for you to remember, because definitely when you will write codes on your own, you will always provide H, because it becomes easier for other address calculations. But during the exam, be careful as to how the origin is represented. So if the origin is represented with a H, so there is no complication. You can, start calculation from the hexadecimal system. But if the address is given in decimal, if H is not specified, then be sure that you convert that number to hexadecimal, and after that go for address calculation. I'm saying address calculation because in your future classes, or as we move on, you will see that a lot of things are related with address calculation. So you need to know the address. Okay, so be careful about this portion, that whether H is present or not. The next part is equate. This is also a directive. I should write over here. Okay, this is also a directive. Equate was also there in our previous course. When we discussed about our 8086 assembly language, microprocessor assembly language. So, when equate directive, it defines a constant value, or it defines a constant without occupying a memory location. Now, most of you might get confused or had some confusion with this thing, that how we can define a constant without occupying a memory location. Okay, so try to hear me out. Directives are some simple directions for the assembler. Okay, whenever we say memory location, we mean the memory location of a mu C. I repeat, whenever we say memory location, we mean the memory location of a mu C. So what is the meaning of equate? Equate means, see, look at this example. So I have written count equate 25. So this line is basically a directive for the assembler. You are telling the assembler that whenever you will find this variable, that is count, whenever you will find this variable, instead of this variable, please use 25. That is something you are telling the compiler. So the compiler keeps that within itself, that okay, within the code, whenever I will encounter count, instead of this variable, I will put 25. Like for this example, in this line, move R3 hashtag count. So your assembler encountered count. So what it will do? It will use 25. So your R3 will have the value 25. So you see that this particular line, that is equate, count equate 25, this one is simply a directive for the assembler. Your assembler is not converting this to machine code. Okay, you are just saying the assembler what to do. So when you're saying the assembler what to do, obviously it will not occupy any memory location in the mu C. Right, there will be no memory that will be allocated for this type of directive, like count equate 25 in the mu C. But when you execute this line, definitely some memory will be used. That is fine. That is a different thing. We are saying that this particular line, or this equate, will not occupy any memory location in the mu C. Is this portion understood to all of you?
Yes, sir.
Yes, sir.
If there is anyone who has confusion, yeah, please ask.
Sir, this 25 is in hex or decimal?
It doesn't matter it is in hex or it is in hex or decimal, because for the timing, if you do not provide anything, definitely it is in decimal.
Sir, and my question is, why haven't we put any hash sign before 25 in count equate 25?
In count equate 25, okay. The purpose of equate itself is to define a constant. So by default, it assumes that this is a constant. The significance of hashtag is to differentiate between a value and address. We never equate an address. Is it okay? For an address, we never use equate. So that's why we do not put a hashtag over here, because by default, it assumes that this is a constant value. Now, how you use this constant value is up to you, because the hashtag will play a significant role over here. So how you use this constant value is up to you, that whether you want to use this constant as a value or you want to use this constant as a specific memory location, that is up to you. But in this particular line, you will always use without a hashtag. I mean, only the value will be equated. Have you got my point?
Yes, I understood.
Okay, any other question? Any
Sir,
other?
so you were saying that the directives are specifications for the assembler.
For the assembler, right?
If I use another assembler,
Mhm.
there I didn't use eq for equate purpose. Let us suppose that I use another word for equate purpose. So that won't make any difference to the microcontroller.
So you are talking about different assemblers, right?
So I am saying that for an assembler, there is eq for equate purpose. If there is any assembler that has some another keyword for equate purpose, it will no difference for the microcontroller, right?
No. For the microcontroller, it doesn't make any difference at all, because this thing does not reach up to the microcontroller, right? It is only within the assembler. So definitely it doesn't make any difference.
Okay.
Right. Any other question?
Can you
Sir,
explain the hash part again? Now, why do you use hash?
Why do we use hashtag? The difference is, when you provide hashtag, it means you want to store the specific value, the numerical value or the number. Okay, that is what we want to move. When you do not provide hashtag, we mean to move the content of the address. Like, okay, so this was, I was supposed to ask this question, but since you asked, so let me explain. Okay, so what is the difference if we do not give a hashtag over here? Say we have written something like move R3, then count. Right, this is an instruction. So this instruction, what your assembler will do, your assembler will turn this into this, move R3 25, because your assembler knows that whenever it will see count, it will put 25. So now you get this instruction. The meaning of this instruction is, your microprocessor will go to the address location 25. So the address location 25 will be accessed, and it will check what is the content in that particular memory location. Whatever is the content in that particular memory location will then be transferred to R3. So your R3 will not contain 25 in this case. In this case, your R3 will contain the content of memory address 25. Is that understood now? The difference between this hashtag.
Yes, sir.
Okay, so if we take an example, say you have cleared your entire MUSI memory. So your memory is clear. In that case, you are writing this like move R3 comma count. In that particular case, your R3 will contain 0. Because you have cleared your memory, right? So all your memory are cleared. Cleared means 0. So all your memory are having the content 0. So definitely the memory address 25 will also contain 0, right?
yes,
Have you
sir.
understood?
Yes, sir.
Okay.
Yes, sir.
So is this portion clear to all of you?
Yes, sir.
Okay. So see, that's why I told that over here we do not give any hashtag. We use hashtag after this, because this will always be a constant. Now, how you want to use that constant is up to the programmer. Now the programmer will use this hashtag based on his requirement. Fine, moving on. The end
Sir,
directive.
I have a question, sir.
Yeah, sure.
Sir, if we, whatever you said, that if we clean all the directories, sir, and then will this command will be meaningful, sir, hash count?
Yeah, it will be meaningful. See, clearing means when you write this code, see, you are writing in a compiler, isn't it?
Yes, sir.
So you are writing in a compiler, then you are compiling the code. After that, you are loading the code in your MUSI. So I am saying that before loading this code, you have cleared your entire memory, right? So all your memory are cleared. Now you have loaded this specific code in your microcontroller. So when this is loaded in your microcontroller, these are simply instructions. I mean, this is an instruction for the microcontroller. So the microcontroller needs to do something. So what will your microcontroller do? The microcontroller, when you write this line in a cleared memory, will go to this address. So the memory is cleared. So 25 address memory will also be cleared. So in that particular address, the content will be 0. So that 0 will be moved to R3. Have you got my point?
Yes, sir.
Okay. Any other question? All right, so let's move on. The last is end directive. Fine, you already know that this indicates the end of the source file, and anything after the end directive is ignored by the assembler. So if in your exam somehow you see some complicated code, something you have never seen in your life, don't get afraid, okay? Just see where is the end directive. If the end directive is before all those codes, you can simply neglect that like the assembler. You can just ignore that, okay? So we don't consider anything that is not considered by the assembler. So the assembler ignores anything after the end directive. So we will also ignore anything after the end directive.
Sir,
Yes.
the permitted are
Yeah, the permitted are, I mean, these are the ones which are permitted. The correct sentence should have been the permitted characters are or something like that. But you see over here in this particular page, your characters do mean something. So that's why it is simply written as the permitted are. So which are permitted, these are permitted, something like this. This page is purely theoretical. There is nothing to discuss. Still, if you want to know something, you can always ask.
Sir, is that underscore or
Underscore,
minus sign?
underscore, underscore. Can I move on?
Yes, sir.
Yes, sir.
Which part of the code is level?
Which part of the code is level? Now I need to go back to the previous class. You remember before
Here,
mnemonics, sometimes we write some levels like here or again, something like that.
For jumping
Yeah,
purpose?
yeah, exactly, right. In case of jump, we use a lot of levels. Now let us discuss about the flag bits and PSW register. So the flag register in 8051 is also called your PSW, that is program status word register. So if you see any of this, either flag register or PSW register, it means both of this means the same thing. So this is an 8-bit register, and this is how your 8 bits are distributed. So make sure you always remember that your bits always start with 0. Like this is bit number 0, 1, 2, 3, 4, 5, 6, and 7. So this is how your bits are numbered. So that's why it is written. Look at this. So CY, it is written as PSW.7, meaning that this is the 7th bit in the PSW register. So the 7th bit in PSW register is called the CY, which is carry flag. Then ACE is your auxiliary carry flag. F0 is available to the user for general purpose. For the time being, keep it like this. RS1 and RS0 I will discuss, don't worry. OV is your overflow flag and P is for parity flag. In this chapter, I mean, as long as we are in chapter 2, we will concentrate on carry flag, auxiliary flag, and parity flag only. When we will go to chapter 6, inshallah, at that time we will discuss in details about overflow flag. All right, now comes these things, your RS1 and RS0. Look at on the right hand side. For the time being, assume you have got 4 register banks. Okay? How we get 4 register banks? What are the 4 register banks? How we are getting all these addresses? It will be clear by the end of today's class, inshallah. For the time being, just know that we have 4 register banks. So there has to be some way by which you can select which register bank you want to use or which register bank you want to access. So in order to do that, we use this one, RS1 and RS0. That is your 4th bit of PSW register and 3rd bit of PSW register. With the help of these 2 bits, we determine which bank will be accessed. Like if you provide 00, bank 1 will be accessed. For 01, bank 1. If you provide 00, bank 0 will be accessed. For 01, bank 1. For 102, for 113. Say for example, you have chosen this bank. So you have given RS1 1 and RS0 contains 0. So in that case, you can access bank 2. That means you can access this memory location from 10H up to 17H. These 8 bytes of memory location can be accessed by you when you have chosen register bank 2. Okay, so if there is any question in this page, you can ask.
Sir, what do you mean by register bank selector bit 1 for RS1 and RS0 bit 0?
Sorry, I think I got disconnected. And I lost all my drawing also. Okay, just a second. Did you get your answer? Could you hear what I said?
No, sir, I couldn't hear.
Okay, wait. Sorry. Just a second. Can you see the screen?
Yes, sir.
Okay. This was the same thing that I just drew. This is from your previous class. Okay. All right. So your question was, what is the meaning of register bank selected bit one, right?
Yes, sir.
Okay. So you see that using RS1 and RS0, we select the register bank, right? So that's why, yeah, this one is your bit 0. Okay. So this one is your bit 0 and this one is your bit 1. So that's why it says that register bank selector bit 1, because RS1 is your bit 1 and RS0 is your bit 0. So that's why it says register bank selector bit 0. Because using these two, you select which register bank you are going to use. So have you understood now?
Yes, sir.
Okay. Any other question?
Sir, for a particular operation, sir, we can use only one register bank, sir, at a time.
For a particular operation, you can use only one register bank. Yes. See, in one register bank, you have got 8
8
bytes.
bytes.
Yeah, 8 bytes of memory, right? So you can have, I mean, you will have access to those 8 bytes. Again, if you want to switch your register bank, I mean, within the same program, you can switch just by changing these values, RS0 and RS1. You can switch between register banks.
Sir, what will be the command for switching, sir?
What will be common for switching? So say you are writing some code. Before that, you have written set RS1. What is the meaning of set RS1? Meaning that it will become 1. Then you have written clear RS0, so it will become 0. Then you are writing some code. After that, again you are writing say clear RS1, clear RS0. So automatically it becomes 0, 0. So after that, whatever you will write, it will have access to this memory location.
Yes, sir.
Okay. Any other question?
So are register banks RAM memory?
Exactly, they are RAM memory. I will discuss in detail. After this page, we will see some examples. After the example, I will discuss about that about this register bank. Anything else? All right. So no questions. So let me go to the examples. Let me stop sharing and let me start the whiteboard again. This is your example 2.2 of the book. Those who have the book, you can see from there. Even if you do not have the book, nothing to worry. Just have your class note, it will be more than enough. So we have got two parts in this example, problem A and problem B. So problem A provides you a code and then it wants you to identify the corresponding memory address and the corresponding data. Okay, so if that is the case, what will be the first memory address? After you have executed this code, what will be the first memory address?
Sir, 050H.
Exactly. So memory is all are in hex and we normally write memory in 4 digit. So let us write like this. No need to provide hex because we know that memory is given in hex. Okay. So 0050. So what will be the data in this particular memory address?
Sir, 0 maybe.
0. What about others? You may try even if you're wrong, doesn't matter. Okay. Until and unless you do not try, you will not know where your confusion is. So even if you're wrong, just try. What will be the
memory
content?
address can hold 8 bits, right?
Yeah, every memory address can hold a maximum of 8 bits, right?
So, sir, it should contain like FCH.
It will contain FC, exactly. So the person who said 0, I don't know what logic you had, but you might clear from here. So you see that the first value that we have is 0FCH and this is well within 8 bits. So the first memory location will have this particular content. Is it clear?
Yes, sir.
So what will be the next memory address?
0051.
Exactly, 0051. So keep saying, what will be the data?
05H.
05. Then what will be the memory address?
0052.
52, right. What will be the data?
76.
76. Then is 0053. What will be the data?
Hex of 28.
Exactly, hex of 28, which is
1C.
1C. Okay, now is 0054. Now tell me what will be there?
ASCII code of S.
Exactly, ASCII of S, capital S, which is 53. So similarly, 5 will contain the ASCII of A. So the important thing is, remember, all this will not be stored in a single memory, okay? Each one will occupy a different memory, because if you convert that to ASCII, it might take up to 8 bits. So that's why this line will occupy 3 memory locations, 54, 55, and 56. And this will be 4D. So if I write in comment, just let me write 1. So this is actually ASCII of capital S. So the same thing, this is ASCII of capital A, and this is ASCII of capital M. So someone had a question that why we need to specify, or what is the purpose? So this is the purpose. If you do not specify the memory, your MUSI will not understand where it will store all these data. So few things might happen. Your MUSI might be powerful enough so that it will not show you any error message, but it will randomly store these values, these data. So then it will be difficult for you to know where you have stored the data, or your MUSI might show some error message as well, because it will not know from where to start. Is it okay?
Yes, sir. Now I got it.
Okay, so that's why you need to provide this initial address, that from where it will start storing. All right, so this was about our first problem. Now let us move to the second
Sir,
problem.
what does DB means?
Sorry, sir. DB.
Yes, sir.
So DB means defined byte. We need to convert all our data into bytes, right? Byte size numbers, because all our memory location are byte size. So that's why we always need to use DB. All right.
Yes, sir.
Now let us move to the second problem. So first of all, let us finish the sum. 1 plus 0 is 1, 1 plus 0, 1, 1 plus 1 is 0. We have a carry over here. Then 0 plus 0 is 0, the carry will come down. Again, 1 plus 1 is 0. We have a carry over here. This carry will come down. 1 plus 0, 1, 1 plus 0, 1. Is the summation okay?
Yes, sir.
Yes, sir.
So now tell me, what will be the value of carry flag?
1, sir.
Okay, 1. Why 1?
Sir, it is the, sir, for the final MSB, sir, the 8th bit It's 1.
I think you got confused with
Yeah, it's not zero, sir. No, there-
exactly. I think you
Sir,
got
can I-
confused.
Sorry, sir.
Zero, sir.
Sir, it's 0, sir. Sorry, sir.
Exactly, it will be 0. Okay. Okay. No problem. See, until and unless you don't say, you will not know where you are having a confusion. So if you say, you will remember. All right. See, why 0? Let me explain. Okay. So first of all, you need to know that this is your digit 0, 1, 2, 3, 4, 5, 6, and 7. Okay. To find the status of carry bit, what you need to do, you need to check whether there is a carry beyond D7 or not. That is the question you will ask. Is there a carry beyond D7? If the answer is yes, your carry will be 1. If the answer is no, your carry will be 0. So now the question is there a carry beyond D7? You see, there is no carry. So the carry flag will be 0. Carry bit will be 0. Understood this carry bit?
Yes, sir.
Okay. Now tell me, what will be the value in this auxiliary carry flag?
Sir, 0.
0. Why? The question is why.
Sir, does auxiliary carry mean the carry bit 2D7?
No.
Sir, one.
So it may be the middle 2 ones, sir, maybe.
Okay, so you're partly there. Okay, so in this particular case, your auxiliary carry is also 0. So let me explain. There are two ways in which you can explain. Okay. First way is you will see when both of the ways actually give the same thing. Okay. You will check whether there is a carry from D3 to D4 or not. So the question to ask is there a carry from D3 to D4? If the answer is no, your auxiliary carry is 0. If the answer is yes, that means there is a carry from D3 to D4, then your auxiliary carry will be 1. You can follow another method, like this is an 8-bit number. Instead of 8-bit, you can consider 4-bit number. So in your 4-bit number, the last digit is your D3. So you can simply apply the same formula like carry. So the question will be, is there a carry beyond D3? If the answer is yes, your auxiliary carry will be 1. If the answer is no, like there is no carry beyond D3, then your auxiliary will be 0. Let me finish. Now don't get confused with this one, because this is a carry from D2 to D3. See, from where is this one coming? This one is coming from here. So this is a carry from D2 to D3. And our question is there a carry from D3 to D4? I hope you have understood this portion. Still, if you have not understood, you can ask. Is it understood by all of you?
Understood, sir.
Okay. So the last question, what will be the value of parity flag?
1.
How much?
1.
1. Okay, why 1?
Even number of ones in the result.
Even number of 1. Even number of 1 থাকলে কি হয়? 1 না 0?
Sir, 0, sir.
Your logic was correct, but your conclusion was a bit wrong. Yeah, it will be 0. Okay, why? Okay. See, the result is stored in accumulator register. That is, register A is known as accumulator. So parity flag will always count the number of 1 bits in accumulator register. I repeat, parity flag will always count the number of 1 bits in accumulator register. So in this accumulator, how many 1 we have? 1, 2, 3, 4, 5, 6. So we have 6 1 bits. So if we have even numbered of bits, parity will be 0 and vice versa. So is this example clear to all of you? Have you understood?
Sir, I have a question, sir.
Yeah. Sure. Say.
Sir, what is the use of a parity bit, sir?
What is the use of a parity flag? There is a lot of use of a parity flag. Some use I know is in your error correction. You know, in telecommunication, when we send data, your parity is often used as your error correction. It is known as parity bit checker or something like that. I don't know whether have you done. Yeah, you are in 4th year, so you should know this. You have completed your telecommunication course, right?
Yes.
So did you not encounter anything like parity checker or parity bit checker, something like that? Anyone? Do you at least remember this parity correction? Of course, you had
Yes,
something like this.
There was a
There were something like this.
Yeah, of course there was. So this parity plays a vital role in that error correction portion. Maybe there are other applications as well, but see, in the course we covered only up to that. So that is what I know for the time being. But of course, it has got some usefulness. Okay. Now, if you ask me that, sir, how parity determines error, now those are very big theories. No, understanding those things in telecommunication was really difficult. But at that time, I think we understood and we enjoyed actually. That was a very, I mean, fun thing to understand that how parity corrects the error and all this thing. For of course, as of now, I don't remember. I need to revise. Then I think I can remember. Okay, any other question? So you understood all these portions, right?
Yes.
So shall we go for a short quiz?
Can, sir.
Okay, actually no, I'll not go for a quiz. I have a lot of things to finish today. I hope you remember that we have 128 bytes of RAM in 8051, right? You remember this question. So now let me ask you a question. So in your RAM, in your 8051 RAM, there is 128 bytes of memory. So if the starting address is 00 hex, what is the last address in the RAM location? So I have written over here having the address 00H. I don't think you can read this. Right again. Having the address 00H. So that is the starting address. So what is the finishing address? Tell me. I'll leave this blank for the time being. Tell me what is the last address?
Sir, 128 in hex.
128
In hex. I
So
don't
what
know.
is that? Tell me that. Convert. Come on. I told you, see it with a
Sir,
calculator.
if, sir.
If. Okay. Any other opinion?
7.
How much? I can't hear. Be a bit louder.
7x.
Sir, 7F.
Exactly. It is 7FH. 7FH. Okay. Did all of you understand the calculation? How we got 7F? So I hope all of you understood. If there is someone who did not, you have to ask. So among all the 3 sections, you are the only section that understood this. I did not, I mean, I had not to explain.
I didn't understand, sir.
Come on, I don't know why you feel shy to ask questions. I really don't understand. It may happen. Some of your friends might know and you might not know. So what's there? You have to ask, isn't it? Okay, I'll explain. Don't worry. You need to understand the small things, okay? Otherwise, if you keep storing these small things, then you'll see there are a lot of things you don't understand. Then it will be very difficult for you. Let me finish writing, after that I'll explain. All right. So the question was how we got this 7F, right? Okay. So we have got 128 bytes of memory. So try to understand the meaning of that. Okay. So we have got 128 bytes of memory. So if this is your first byte, so let's say this is your first byte. And remember, each byte has 8 bits. So if this is your first byte, what is the address of your first byte? The address is 008. Okay, now let us go to the second byte. If this is my second byte of memory, that is second byte. Okay. So what is the address of this memory? 018. In this way, I will have 128 byte. If I follow the same manner, what will be the memory? So how are you calculating the memory? For the first byte, you have 008. For the second byte, you have 018. So what are you actually doing? You are subtracting 1 and then you are converting that into hex. That is how you are finding it. So what is the last byte? 128th byte. So what you need to do? Subtract 1 from here. Why we are subtracting? Because we are starting from 0. But over here you started from 1. But while addressing, we are starting from 0. So if you subtract 1, you end up getting 127 in decimal. So if you convert that to hex, you end up getting 7F in hex. So that is how your starting memory address is 008 and your last memory address is 07FH. Did all of you understand now? Have you all of you understood now?
Yes, sir.
Please make sure you understand, okay? Because if I'm taking effort to explain you, you also have to put effort to explain me. So it will be bidirectional. So make sure you understand. Whatever I have written over here, I mean in black colored, this thing, what red is just for discussing that portion. I will describe this thing with the help of a diagram. So let me know when you're finished writing this thing. Once you finish writing, please someone at least inform me that sir finished writing.
Finished, sir.
Okay. ID 1056, are you there? 1056.
Yes, sir.
So can you explain me how we got 7FH?
So this is further from 0, it is 127 distance.
If you want, you can explain in Bangla also, but explain me how we got 7FH.
So 7F actually, sir, distance from 0 and 7F H is 127.
Okay, so that portion you are correct. Distance is 127. So if I give you the starting address and instead of 128, if I say that it is 130, so in that case, what will be my last address?
So it would be 82.
81. It will be 81.
81.
I hope you understand. Okay, thank you. You may mute yourself.
কাজ হলো 5 মিনিটের ভাই।
Try to draw this figure with me. Okay? All right. So this is how your 128 bytes of RAM memory is allocated in the RAM. I mean, this is how this is distributed. And I talked about register bank when I discussed the flag register. So you can match with that. Okay. So this is how your memory is divided. So see, this portion, these, okay, these are your register banks. Okay. We have got 32 bytes of memory allocated for this register banks only. And this register bank is divided into 4 registers, bank 0, 1, 2, 3, each containing 8 bytes of memory. And among these 4 register bank, register 1 is specifically known as stack. Okay, you know what is stack, and we will discuss stack in the next class also, inshallah. But know that stack is basically nothing but your register bank 1. Then we have got bit addressable RAM. Actually, these are, I mean, needed for our read and write memory and all these things. We will discuss this when we go to chapter 8. And then finally, we have got our scratch pad RAM. This is also used for some extra memory if needed for some other register banks. We can use this as an extra memory. Or at the same time, when we connect various input output ports, or we need to store data from the memory, from other memory, or from, I mean, we are reading data from some sensors which are connected to a port. All this type of data can be stored in this scratch pad. I mean, you will come across this as we move on. For the time being, just focus on these 4 register banks. And of course, you remember that how we select register bank using RS0 and RS1. So using these 2 bits in your PSW register, we can select which register bank we want to access. And while we were discussing your flag register, if you go back to that table, as I don't have the class note over here, so if you go back to the table, you will see the address are exactly same as the address I've written over here. So exactly same 8 bytes are provided to each bank, and this is how your entire 128 bytes is distributed within the RAM. So if there is any question, please you can ask now. No question? So if there are no questions, I hope you understood everything, which is very unlikely. The other conclusion is you have understood nothing.
Can you elaborate a bit about scratch pad RAM, sir?
Yeah, sure. Why not? You know, scratch pad RAM. So the name itself suggests that this is a scratch pad, right? So that means you can use as rough or something like that. Basically, your scratch pad RAM is normally used when you need some extra memory within the register banks. So you have register bank 0, 2, and 3. So suppose you are using register bank 2, suddenly you need some extra memory. So in that case, you can use scratch pad RAM. That is one of the function of scratch pad RAM. The other function is you will, when we discuss about your 8051 MUC, you remember that it had a lot of ports, most probably 4 ports divided into 32 pins or something like that. So you will see that you will connect various devices or peripherals with those ports. So in order to read data from those ports, sometimes you need to read data from the ports and you need to store the data. So to read and store data from the ports, you will need that scratch pad RAM. That is where you can store the data. Is it? I mean, if I just generally say, then I can say that you can use scratch pad RAM for any purpose. That's why 80 bytes are allocated for that. But all the others have got some specific purpose, like stack has a specific purpose. You cannot use stack register. I mean, you cannot use register bank for other purpose other than stack. Okay, then bit addressable RAM, when we will go to chapter 8, you will see that it has got some specific purpose. Other than that purpose, you cannot use that portion of the memory. But scratchpad is your general purpose. You can use for most of the things. Okay?
Okay, sir.
Any other question?
Sir, what are the purposes that we refer to general purposes?
general purpose is, suppose you have connected a sensor with your microcontroller, and that sensor is designed, okay, you have written your code such a way that you will read the temperature, say there is a temperature sensor, you will read the temperature every 1 hour and you will store that. So, and you have connected that for 1 day, so 24 hours. So where do you store that temperature? Tell me. So this type of particular thing, these are known as general purpose, not specific purpose. These are known as general purpose. I mean, general use, normal use. So all these type of general purpose things or general purpose data will be stored in your Scratchpad RAM. Is that okay?
Yes.
Okay. I got a very big message. I was still in the whole class. My phone is out of charge and there is load shedding. Get a full, yeah. Hassan Jamil. Okay. Please remember Hassan Jamil is present. Okay. Even if I forget. Okay. Any other question? I'll take the attendance right now. Okay. Is there any other question?
No, sir.
No, sir.
If there is no question, then I may stop sharing. You may also stop recording. I'll just take the attendance.